this is where we were last time. So we had established a relationship between distributions, between observed distributions. One of them was supposed to be completely without selection, just neutral evolution. One of them was under selection. Both are equilibria, but they're different equilibria, and the difference is what physicists would call a Boltzmann factor, which is just the exponential of the product of the inverse amount of noise, which is our population size, and this potential landscape where our dynamics is taking place. So you can look at relations of this sort in three different ways. You can say, well, this is an information theoretic relationship, right? There's two distributions, and there's a relative log likelihood giving the difference of these distributions. And as we have seen, that means that if I integrate this ratio, this log of this ratio, which is just n times f, if I integrate this, then I get n times the expectation value of the f, and that is just the definition of the Kohlberg-Leiber distance between these two distributions. We can look at this as an evolutionary relationship, and then this object here in the exponential is the fitness. So it says something very simple. It says that, is there something right? Yeah. It says that essentially the distribution of our populations are going to be somewhere close to the maximum of this fitness landscape, up to sort of a 1 over n tolerance. That's as much as this noise is able to drive the population down from the peak of this fitness landscape. And clearly, as if I make n smaller, the noise is going to increase, and the entropy of this distribution is going to increase because it's going to be less spread out away from the peak of this fitness landscape. And if I look at this as a physicist, and if I for the moment forget about this prior distribution P0, if I assume that this is a constant or a flat distribution, then I would just read this as the Boltzmann distribution of equilibrium statistical mechanics. And if I permit myself the liberty of thinking of this f function as a potential energy, whether or not that analogy is completely correct, we're going to see a little bit later. But we're going to play with exactly this kind of translations between the fields. And I remind you, of course, what we have seen last time, all this comes just out as a simple, wouldn't the Boltzmann distribution have a negative ratio? Oh yeah, that's right. So you should also put a minus sign in the definition. So what were peaks of this fitness landscape will now become minima of the energy landscape. Thanks for this. And so all this, it comes out as from the basic mathematics of this Fokker-Planck equation. I just remind you that if you have a Fokker-Planck equation where this drift field that gives a deterministic equation, this S of x, is the gradient of a scalar function f, then it has an equilibrium distribution, which is the exponential of f multiplied with the strength of the noise by what physicists call the Einstein relation. So this is all that there is behind. But we know, of course, then that this solution satisfies an extremal principle that among all the distributions that have constant entropy, the one that is chosen by this actual dynamics is then the one that maximizes the expectation value of this fitness. So you can say that this dynamical formulation gives an interpretation to these information theoretical quantities.
The first formula, we can see that in the maxima of f, and as the number of population increases, n increases, it seems that the equilibrium probability grows bigger and bigger, and the probability of the population to stay at that maximum increases.
Yeah.
We're told that it will get down one by.
Yeah.
Is it consistent? It is as n increases, I can see that the probability that it will stay at the maximum.
Yes, that's right. So if you make it larger, conversely, then the noise will become less and less important, and in the very end, you will have a delta distribution at the peak of this fitness landscape. That's sort of the deterministic limit. We're actually going to see that. So let me just conclude what actually was the still is part of yesterday's lecture to show you that this kind of things can actually be useful for learning something about fitness from genomic data. So we said the system that we're going to look at is this very simple system, this very simple genomic system of 10 binding sites. Of course, we know something about the statistics of these binding sites by making alignments, just in the way that Eric has discussed them, of many of them, and get position-specific weight matrices, so that we know something about the probabilities of letters at a given position. But independently of that, for each binding site, we know something biophysical. This sequence binds the factor with a certain energy. We're going to take that energy as a sort of summary statistic summarizing this genome information into one real number. You see that this is on practical purpose. So this is what biologists would call a phenotype. In this case, a molecular phenotype. It's something that summarizes this sequence information into one number. Why is that in this case a reasonable thing to do? Well, because we think that the sole reason, the sole functional role of these 10 base pairs is to bind that transcription factor. So whatever fitness I assign to these 10 letters here should be mediated by this function E. Because biophysics tells us that this binding energy is the effective quantity that governs how much this transcription factor is bound. So, of course, just a quick reminder about the biology. In higher organisms, it doesn't look like this one binding site. It looks like this in front of a typical gene. So it's a much more complicated problem with many sites and interactions and so on. So we're not going to tackle that problem. This is just a reminder that, you know, if you look in biological system, it often doesn't look like this, but it looks like this. So we're going to go back to this system, and this is a reasonable starting point for thinking about bacteria, for example, where the single binding sites and the transcription factor binding, this makes a function. It is still a reasonable model in organisms like yeast, which look in many ways more like prokaryotes than like these higher eukaryotes, where this is, for example, a sea urchin. So, if we go, in this case, to the yeast genome, and we do this, now we do genomics. So now we forget about all this Überbau of information theory. We just take our window of length 10, we slide it over the intergenic regions of, in this case, Baker's yeast, and we record in every window, which is like the 10 letters. We use our learned function E of A to compute this value of E, and then we shift the window by one base pair. We get new 10 base pairs, we get a new value of E, and then we get a histogram of values of E, and that's what's shown here. And that's what we are more or less going to identify with our background distribution, not under selection, because most sites do not bind a given transcription factor and should be random with respect to binding that particular transcription factor. They can do lots of other functional stuff. And indeed, you see, if you just compute this from random sequence, and that then in first approximation, the bulk of this distribution, you should think of this as a binomial distribution or a Gaussian distribution. And indeed, on this semi-logarithmic thing, this looks very much like a parabola, as it should. But then you see exactly in this region where biophysics tells us that there should be binding under physiological condition, which in our normalization here of the binding energies, this interval between 0 and 1, there the distribution looks slightly different, the distribution that it observes counts in the genome, which is these black dots. There is a little secondary peak. So we can actually, and this is a little bit of simplification, what I'm doing here, but it's not too much a distortion of the truth. You can decompose now this distribution of genomic counts into a superposition, into linear superposition of this bulk behavior, and sort of what you would see if you extrapolate this, and then these extra counts you associate with this distribution Q of E. Now you have to normalize both of these distributions again. That's what we are told in information theory. And then you form this log likelihood score. And now you have learned the fitness function from this genomic overrepresentation, from the fact that populations tend to be, are more likely to be at close to the peak of such a fitness landscape. Well, and if you just take this thing, this is how it roughly looks like. This fitness landscape is not completely unreasonable. It looks like something that is a monotonically decreasing function. And so on average, if I make a binding site stronger, it will have a beneficial effect. So what this means now is verbatim a representation of fitness. So if I make a mutation in the binding site that changes my energy from E1 to E2, then I can read off sort of the effect of this mutation on the horizontal axis, and this landscape tells me what the growth rate, the expected growth rate difference for these two subpopulations with these different functions, these different binding sites are. Of course, there's a couple of assumptions here, right? So we lump all the binding sites of a given factor into one statistical class. We're sort of doing a kind of more or less uncontrolled average over all the instances of these different transcription factors, but we have learned something about selection acting on the system that we can test.
I don't want to hold you up. I want to make one comment about this, and that is that this transcription factor is kind of special in the sense that for most transcription factors, you don't really get such a nice bump that allows you to make such a nice decomposition.
Very, very true, and thanks for this comment. This is, of course, a textbook example of this, right? So many, because it's a transcription factor. First of all, you have it's very pleiotropic. It means you have many binding sites where this is acting upon. So it can do statistics. There's other transcription factors where you just have a few. So your position-specific weight matrices would have just much bigger error bars. You wouldn't know this function E of A very well. Well, maybe you can overcome this by now, measuring it directly in a microfluid experiment. But then still, if you do the genomic analysis, this extra peak here wouldn't stick out from the blue background, because this still only works if it has a few hundred counts. So you can see this extra little bump. If that transcription factor is only 5 binding sites, but good luck with seeing that in the tail of this background distribution. So this doesn't work for all transcription factors, this way of inference. It tells us something of how we can think conceptually about selective effect on these transcription factors, but the possibility of inferring things in this way, that's limited to examples where we have enough counts. So, but then you can predict now something. For example, you can now go and now you can go back to the dynamical model. You can say, we should know how, if I start at a given value at a given initial sequence, or equivalently at a given value of E1 in one species. Now I let this evolutionary dynamics run. The evolutionary dynamics is just given by our Fokker-Planck equation. Right? So now we start from an initial condition, we wait for a time delta t, and we see how sequences have evolved, and hence how these E values, how these phenotypes have evolved. And of course, the longer you wait, the more is the average mean square deviation from this initial value, delta E. So at time t equals 0, this would be a delta function to 0. And then as you wait, and these are 3 neighboring yeast species, then this becomes a broader and broader distribution because things diffuse in this fitness landscape. So if you started at one value, say here, you might go a little bit up or you might go a little bit down, but your mean square difference to the original value goes down. So this is on the basis of this model, best estimate of the finite time dynamics. And that works well. So when we did this first, there was a big discrepancy between what we got actually from these genomic counts, which were sort of this light distribution, to what we got from our model. But then sort of, this is just another little reminder of all the bioinformatic nuisances that are in the actual genomic data. Then it turned out that all these extra peaks, these are actually sites that overlap with another binding site, of which there are many in the yeast genome, because the yeast genome is rather packed with functional elements because it's still a relatively small genome. Now, if you filter those out and take the sites that are alone, which don't overlap with anything that also has to do another job, which of course leads to another dynamics, not predicted by our model, then you find something that is quantitatively giving the right distribution of this actual evolution across species. So, so much for, well, and let me skip in the interest of time this slide and move to what I wanted to move next. And so I want to ask something that is potentially interesting from an information theoretical point of view, because that way of thinking about systems is maybe is in all these fields, including statistical physics, is just being developed. So what if we, in the current or the previous example, we dealt with an equilibrium situation, which was an assumption. So it may or may not be the real system, an evolutionary equilibrium. And in an equilibrium means that the dynamics pushes the system up and down in this fitness landscape, and hence there is some kind of information theoretic optimization that I can think of this problem of dynamics in the fitness landscape. But the landscape itself doesn't move. Right? But now we want to think of systems where the landscape itself is moving. So can we extrapolate this information theoretical or statistical physics or evolutionary way to non-equilibrium situations? And of course, they are ubiquitous. And so say for your problem, it would be something like, what if the rules given to the monkey keep changing, and it has to learn something, but it isn't sure about whether the same rule that it has just learned is applied. Now, of course, we know if you change the rules very quickly, then it's just as good as having no rule at all, because you can't tell for the next trial what it doesn't even make sense to learn the previous rule, right? Because it doesn't apply to the next trial. The interesting kind of things is when the rules change about at the same speed as we can learn them. So we can still follow this mountain, but we always are never really on top of this mountain, but we're somewhere sort of lagging behind the moving mountain. And one of the systems that we got very interested in, that will be most of my talk tomorrow, on Tuesday, will be is the genomics of the influenza virus, because that's exactly such a system. This virus needs to attack us every winter afresh, but our immune systems get better at fighting this virus. So you can convince yourself that this virus would be dead if it doesn't continuously sort of learn our immune response and adapt to it. And so this co-evolutionary, strongly non-equilibrium process, and you can see already from the sort of, well, I'm going to talk about this system more tomorrow. This is just a motivation of why we should think of non-equilibrium system as something important to complement our sort of information theoretical or statistical physics, or however you want to call it, way of thinking about them. And of course, first of all, to think about them. So already Fisher, the great sort of one of the theoreticians in the 30s and 40s, thought about this, and he had a theorem about this evolution under natural selection, which describes the deterministic evolution of it. And you will immediately sort of recognize this as also like a simple property of the deterministic limit of this Fokker-Planck equation. Namely, if we have no noise, right, if you have only deterministic evolution, So if we go only up this landscape, then the change in fitness is always positive, and actually it's just the square of the local gradient of this function. And why, of this fitness function, why is it the square? Well, it's the gain in height multiplied by this response coefficient, which is the self-linear function of gradient f. So that is just gradient f squared. So it's the important thing. This is always positive, right? Because this is a square on the right-hand side. So the mean fitness will always increase if I make deterministic movements on this landscape. Easy. So Fisher was very proud of this. He called this modestly the fundamental theory of natural selection, because he thought that this was not only the greatest thing that he did on evolution, he thought this was one of the greatest things that anybody could do ever on evolution. But so actually this theorem has a very interesting story of scientific reception. Nobody understood this theorem well, and there was a literature going over 50 years, what Kimura could have thought, what Fisher could have meant with this, and so on. So it was a very interesting story of reception. And one of these sort of points of misunderstanding that I think was key, why it was so much misunderstood, was that this is essentially, this turns out to be a non-equilibrium relationship. It does no longer depend on equilibrium, and so it actually there is still a quantity whose time derivative is this square. If you think of the same process in a moving fitness landscape, but it can't anymore be f, right? Because you can see that in a moving mountain, you can keep on following this mountain going up the slope, but the mountain is moving and you don't have a net increase in height. So you move up the mountain, but you don't increase in height. So the question I want to pose, or the answer I want to give, is what is here on the left-hand side of this equation, and how should we define this thing that keeps increasing even if the mountain is moving? And I think the problem of Fisher's formulation is that he thought of this object, but he used the terminology that at the time was available, and it was the one of equilibrium statistical theory. And that was a good part of the source of these misunderstandings. Of course, now we are nearly a century further on, and we have developed non-equilibrium statistical mechanics, and a lot of the notions have been sharpened in the 90s with interesting new work on non-equilibrium statistical mechanics, and we can again ask these questions now for evolutionary processes. So let's define what this left-hand side might have been. So what happens on a moving mountain? So now we want to think of all these, we want to try to think of these quantities also in information theoretic terms as we go along. So now we follow this system over a whole trajectory or history, and so we imagine we had a set of measurements of all these frequencies at times t1 up to t8. So now we look at the whole history of a system that moves up or maybe down, and so we have these genotype distributions measured at different times. So now here's my definition of what this left-hand side is. We just sum up the changes in these x's multiplied by the local gradient. And as we already mentioned yesterday, you don't need to think of this for most of what I'm saying as a gradient of a scalar function. Any vector field S will do, even if it has a curve. So our definitions don't depend on that. So we really just multiply our local changes in x to delta x for each time step, multiply them by the local gradient, and then we sum this all up over our entire trajectory. So what do we get? Well, that's very easy, right? So if now, for the purposes of this picture, if this vector field is really just a gradient of the scalar function, we just get the local increase, the delta x multiplied by the local slope is the local green arrow. We add up all the green arrows, so what we get is the gain in fitness, the gain in height on this landscape between the initial point of this trajectory x0 and the final point xn. Trivial. Now, the point is, what happens if this landscape is moving? We can still define this thing in exactly the same way. There's nothing wrong with multiplying the local increments delta x times the slope. The only thing that changes that this is no longer equal to the difference between the final f value and the initial f value. So, but we still keep our adding up our green arrows here, and it's still the local thing that we traveled up this landscape. The only problem is that the landscape, if the landscape moves at the same time, so here's the initial landscape, next time point, third time point, then we might lose height because the landscape sort of sinks down beneath our feet. And we keep moving up, but we don't get anywhere in absolute terms. But this definition of this flux doesn't care. You could, or it's just like moving on an escalator, right? You can. There's something that you gain in height or lose, but it's not related in a simple way to the amount of steps that you step up on the escalator. So now, why did we introduce that? Because this quantity actually. So let me introduce one more thing, right? So if we now go backwards. So now here's the forward movement, and we take exactly the same backward history. So we just play the film backwards, including, of course, the movement of the escalator. Right? So our movements and the movements of the escalator are both played backwards. And so then you start here at time t0, you go first down and down and down and down. So this quantity phi is exactly its negative, because all the movements and are just in reverse order. So that's obvious when you play the film backwards. Now, now we can try to copy our equilibrium way of thinking about relative entropy. Right? So what can be shown is that the probability of this backward movement is the probability. So now our probability space is different. It's no longer the distributions, but it's entire histories. So now we try to make an information theoretic calculus on the entire histories of this non-equilibrium process, and the probability of each history is in a simple way related to the probability of the backward history. I'm going to come to. So this is one of these achievements of non-equilibrium statistical mechanics that has been done in a different context, which I'm going to come in a second. And so here, the analogonous this is there's still an n here, but now this fitness flux is taking the role of fitness. So this means if we compare the probability of observing this movement with the probability of observing the backward movement, then that has again like a Boltzmann factor, but now it's no longer the fitness, but this entire fitness flux. So if this fitness flux is zero, it means that it's exactly as probable to observe this backward movement. This fitness flux is different from, is larger than zero, and the backward movement is less likely. So this is a measure, if you will, of how much you can tell whether this movie is played in the right direction. So, and then there is a boundary term that is the entropy difference of initial and final condition, which is here plays a role of a boundary term. So there's one more term in this equation. So,
Where does that come from?
well, I'm going to show you the next slide of what this comes from. And the next couple of slides. So if we think of this now, so this was the probability of a given trajectory.
I meant the boundary term.
Oh, the boundary term. The boundary term comes from, well, because we have like an information on the so.
Is it essentially the fitness of the first and last?
If it were equilibrium, it would be the fitness. But it can now be any initial distribution, be it in equilibrium or not. And then you can still, of course, calculate this relative entropy, but it does no longer have to be related with fitness. If the initial and the final state are two equilibria, it would be the mean fitness, as we've seen in one of the previous slides. And so this is really just what is very familiar to physicists, right? To calculate the probability of being at this point and this point, we calculate the probability of the initial state times the conditional, or the propagator. And this is the propagator term, and this is the initial condition term. And I also have to compare this for forward and backward. That's why there's a delta H. So this is why this boundary term appears. But so this means that if you neglect this boundary term at the moment, this difference here is, apart from this boundary term, the fitness, the expectation value of the fitness flux is now also interpretable in information theoretic terms. It's the relative Kullback-Leibler distance of the actual process compared to the backward process. That's essentially saying, so I play now many films of forward and backward processes, and how much more, what's the relative distance between this in the information theoretical sense. Of course, that's not quite as useful as the information, as the equilibrium relation, because of course both of these are complicated quantities. I know something that relates one difficult process to another difficult process. It's not exactly giving us the distribution, like the solution, like in the equilibrium case. So, but now, and this is mimicking, well, I'm going to come to the parallels with statistical mechanics, but if I now just sum these probabilities of all these backward processes here, I get 1. Now I make the summation over all possible trajectories. And on the left-hand side I get 1, and hence I get that an integral over all possible histories, or in physics term a path integral, all these possible paths multiplied by their probability, multiplied by this object, which is just the expectation value of this object, is 1.
That's why you're Feynman's picture then.
Sorry?
That's why you're Feynman's.
This is why I had Feynman's picture, and this is what I don't understand to date, that kind of properties of statistical mechanics, now not of evolutionary theory, but of ordinary statistical mechanics, was so close to what Feynman did on quantum mechanics that he should have thought of these points that came up in the 90s as under Jaginski's theory in the non-equilibrium relations. They are essentially nothing but the Feynman calculus of propagators. But somehow it's another irony of the history of science that this happened 50 years later.
Well, it's funny because, I mean, there was already quite early a realization that if you make time an imaginary quantity, then you really map the path integral to a statistical
Very much so.
average.
That's in Feynman's books on path integrals, for example. That mapping was very well known. This is a big quotation, right?
Yes.
But somehow you see that the problem is, of course, if you think of this in terms of quantum mechanics, that everything remains the same, but there would be an I. And that means we have essentially time reversal symmetry. Right? If you put an I in this, then time reversal for quantum mechanics is just complex conjugation. So the question that we are asking here doesn't make sense, right? About how much more likely some forward process is with respect to some backward process. So that's why for quantum mechanics, Feynman didn't have to ask that sort of question. But as soon as you take away the I, you can ask these questions, and they have been answered in the 90s. So we get a relationship, a very complicated sum of this complicated observable, evaluated over all the possible histories of our past, is 1. This is a theorem. Now, a theorem is probably true if we didn't make a mistake. It doesn't mean yet that it's useful for anything. And so let's see whether this could be useful for something. I claim it's useful for biology primarily in helping to give us the right measure of non-equilibrium processes. Of course, a lot of other related things as well. So let's make a simple application of this. Let's apply Jensen's inequality, which I remind you just says is that the expectation value of this thing in the exponent here then satisfies an inequality. And this inequality is the corresponding log. So you take the logarithm here inside the bracket and the logarithm here. And so this is no longer an equality because you have exchanged formation of logarithm and formation of the average. But essentially, just because the logarithm is a nicely curved function, then you get this inequality. And this says that the expectation value for any process is larger than this delta h, which is our boundary term. So that means, for example, if you look at the case of influenza, and if you have any process of this sort in mind, where it's a steady state process, where the escalator moves with a given speed, or the mountains we try to follow, then in any stationary process, this boundary term is 0 because our probability distribution is a stationary distribution. And hence, in any such stationary process, I mean, if you think of influenza, this looks pretty much like a stationary process. Then it keeps producing a positive fitness flux. So this fitness flux is a quantity that is almost universally increasing, even in non-equilibrium situation. There is no assumption of equilibrium here anymore. In that sense, for non-equilibrium situation, it's more fundamental than fitness itself, because there's no such growth law for fitness. So you can look at equilibrium. There's of course the fitness flux is 0 because you go on average as much as you have no moving mountain, and then stationary non-equilibrium. So on, you can discuss other non-equilibrium scenarios.
X-axis, y-axis graphs.
Sorry?
What are the x-axis, y-axis of the graphs?
Well, so here this is a function of time. So and then you can, for example, study this with simulations, and you see how this fitness flux goes. Is a stochastic process, but on average it goes up.
What does red and green mean? What does red and green mean? Red colored curve and green color.
Well, so let me skip this because it's a bit too. I'm happy to show it to you.
So I have a question.
Yes.
In the language of your escalator analogy, you're talking about this escalator is moving and so on. I can imagine situations where the movement of the escalator, or rather the state feeds back to the movement of the escalator. So the escalator movement is not a constant movement. It depends on where you are in the state. Is your formulation?
Yeah. It doesn't make. It's not. It then may not be a stationary state,
Right.
but the general sum rule, and that was the strength of these developments in statistical mechanics, holds under no particular assumptions. So let's take the last 5 minutes and just try to make a little dictionary. And this is for the physicists. Now maybe interesting. You think, well, now if we take this third way of thinking about it in terms of statistical physics, is fitness energy or not, and what does it have to do with our information theoretic setting? So here is our little dictionary. So fitness, we said, is up to this minus sign. It looks like, if we take this Boltzmann distribution, you could say, well, it looks like this thing which is in the exponent of the Boltzmann distribution, and the energy. So the equilibrium is then just, well, here is nf e to the nf of x, up to this prefactor p0, which is a constant here, we have an inverse temperature times e, and there's still the minus sign. So inverse temperature, the same as the analogon of populations. Ticked off. Then, our quantity, this fitness flux, turns out to be exactly what would be the heat transferred from the system to a heat bath in the setting of statistical thermodynamics. And that's pretty obvious here from this formula. It's the amount you slide down the energy landscape times the energy you actually lose, and that, by energy conservation, is the thing that goes off to the heat bath if you take a stochastic trajectory in a thermal system. So, ticked off as far as our dictionary is concerned. Entropy is entropy. Right here we have a prior distribution P0, which is constant here. Apart from that, that gives another minus sign because this relative entropy has intrinsically another sign in its definition than the bare Shannon entropy, but ticked off. So, our fitness flux theorem is nothing but a reformulation of these Jaginski type of equalities that got famous in statistical thermodynamics over the last 2 years. And here the analogon is we just now take this reverse translation. This boundary term is the delta S term of the initial and the final state, and this phi is the Q. And this delta S term and this particular linear combination you can rewrite in terms of a free energy change. So then Jensen's equality on both sides gives here our increase of this phi up to this boundary term, and here it's the this is the entropy, this is the heat flux, this is the entropy change, noting that the heat flux is the entropy increase of the reservoir, of our heat reservoir. This is just a change in total entropy, and of course we know from the second law of thermodynamics that this has to go up. So, translation done. It's fine. But now you should think, well, this is complete nuts, right? Because after all, this is not the same process, right? This is thermodynamics. Entropy increases. This doesn't go backwards. But this is not about the increase of this order. This is supposedly the increase of order. So we got exactly the same relationship here, that something increases with is just a total entropy here on this side. So where does our formalism reflect this thing that these are two completely different scenarios? One is the increase of information, the other is the increase of entropy. So what have we done wrong?
Is it because F and E have E that is minus, right?
Well, then, the minus, but the minus is just if everybody in physics had decided that the ground state is a maximum in entropy, energy, the rest of physics would go the same way, right? You have a couple of minus signs in other places. That's a choice. But so there is one thing which is not a choice, which is different. We were sloppy in saying that the fitness is the energy, and let's see what we discover. So in physics, we know that there's conservation of energy. So that means if I take all my systems of all the energies of all my trajectories and I add up E0 to them, nothing is supposed to change. Right now, for our fitness landscape, it's something else. Because only gradients in this fitness landscape matter. So we are allowed to add a new normalization to this fitness landscape at every time point independently. So nothing about the time dependence on our fitness landscape is supposed to enter our theory. We can say, if I take a real seascape, this dynamic landscape, which I like to call seascape, and the water has risen by 10 meters the next day. This is pretty observable. We call this a tsunami, and it's not good. Right? So in our fitness seascapes, there are no tsunamis. If the next day everybody has a fitness plus 10, it is absorbed in the normalization constant because all growth rate differences will be exactly the same. So we have an extended, what physicists would call gauge symmetry, gauge invariance here that we don't have in this problem. And this means that a lot of things that we can compute in statistical mechanics, we cannot compute on this side. They make no sense. Everything that has to be to do with partial derivatives with time, with respect to time of our fitness landscape, doesn't work. In particular, there's no energy conservation. So this is where our dictionary fails. And this is why we are just looking at different quantities. Right? Here, in formulating the second law, we look at the sum of the entropy of the system and the heat bath. That quantity doesn't make sense if you don't have a conserved quantity, because the notion of a heat bath doesn't make sense. And what we're computing on the right-hand side is not the total entropy, but only the entropy of the system proper. And that, of course, can perfectly well go down in a process, because we would just call this a dissipative process. The entropy of the system, of course, goes down as it slides down towards lower energies and dissipates things. It's only that this entropy reappears in the heat bath, and a larger entropy increase has to appear in the heat bath. But the entropy of the system proper can go down and will go down as things slide down energy landscapes, or if you introduce the minus sign again, as things go up in fitness. Final slide, we can compute this decrease in entropy, this opposite second law of thermodynamics, the increase in order, for example, from the position-specific weight matrices of a transcription factor binding site. So now, if I look at now in this graphical thing, so here's the background sequence, which approximately equally distributed probabilities. So these four probabilities that in this logo, this means quarter, 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 quarter. So then this binding site wants other letters with other probabilities, and hence, so the typical information gain or the typical Kullback-Leibler distance to background sequence is about 1 bit per column. And so a typical information gain or entropy loss of a binding site in a prokaryote is of the order of 15 bytes. Bits. So that means this, how much things go down. For some cases we can compute. Embarrassingly, you can't compute at all. So you could ask, so how much is the whole genome? How much information does it contain? But we don't quite know. That has to do with the fact that we don't quite know what fraction of the genome is functional. Particularly in higher organisms, it's still a very debated question, and there is lots of things that could contain some unknown bit of information, or could be essentially background from this information theoretic point of view. So only for these lucky sub-cases of the genome, we can put numbers on how much information is in these letters.
Yeah, I think once one goes to whole genome, one also has to wonder about the setup, because the space becomes so much bigger than what one samples, right? So for one site or a few sites, it makes sense to think of that you're sort of sampling the space. For the whole genome, it doesn't make any sense.
The sampling doesn't make any sense, but you could still, for example, you could still think how much more constrained would a typical color be. And you could, for example, if you do in-depth, deep sequencing, you could try to statistically relate this, for example, to polymorphism statistics. And so, in principle, you can still ask the question how much information is in a given letter. Although, as I agree with you, you would have to renegotiate how to measure that. You can't just do a line here. This thing is, taking the 200 binding sites of ADF1 and writing them in one alignment and then counting. You can't do that for other things for which you don't have the advantage of having 200 comparable units that you can take from the same genome and write beneath one another.
Well, I think the crucial thing is one has to assume something about how the fitness of the entire genome can be decomposed into the fitness of these
Oh yeah,
elements.
so you're right.
That's some.
But even if you don't even talk about fitness, but just about, say, information theoretic constraint. So how much, if I let this thing evolve, how much would the letter at some position change on average or not? Of course, in a motif, it wouldn't change so much because basically this position can only choose between T and C, and A and G are very improbable, whilst in the background it could, on average, change more. You could hope to see signatures of that, for example, in polymorphism statistics and so on. But I agree, so how to do that in detail would be another story. So I think my time is over. I think my slides are also over. So I'll do this summary next time. Thanks a lot.
Actually, I like very much cases where you can find these kinds of analogies because then you can import intuition. But just a comment over here that the formal analogy to this sort of Boltzmann weight, whether it's fitness or fitness flux, is only true in a limit of population genetics where you have only single mutations that reach a fixation between and
very true
time and events.
So when you take, well, actually, so what I've shown you about binding sites was using this low mutation limit. So that means that this entire genotype distribution collapses within one population, collapses to a delta distribution, and we can think of a population being a point hopping up and down on this fitness landscape. That's this low mutation regime that you are referring to. But the general formula actually on this genotype distribution, this holds for even if the mutation rate is not low. So you can generalize this. But the inference that I've shown you for binding sites rests on this low mutation regime. And that's why we could sort of, a single population was in a single genotype or a single value of E. And then we just could put this, we didn't have to evaluate sort of a whole population.
But do you think these analogies survive more or less unchanged even in the more general?
Yes, they can be generalized. So the basic formulas that I've shown you are not limited to this low mutation limit. And you can go sort of to the quasi-species on the other side when n drops out of this equation. It's only a balance between selection and mutation.
You need this curl of the neutral dynamics to vanish, right?
Right.
It's not entirely clear to me what that implies.
That's not entirely clear to me either. It's probably this, well, it is clear in this low mutation regime that we were just discussing, because there it's a property of substitution rate. It's probably a quite benign assumption. It's like what is in all these effective models of sequence evolution is that they have a detailed balance state. No, so that they don't create sort of at the level of substitutions back into the circular currents, which you can do with 4 letters, right? You could go around all the time, but in the neutral dynamics. But all the standard models don't have that, which doesn't mean that the real process doesn't have it, but it's probably a small effect. What it means at the level of polymorphisms within one thing, there you can show that the standard models have actually a small curve. My take of this is probably a nuisance effect that doesn't have a lot of biological meaning, but I don't really quite know. So here, the assumption is that the neutral process doesn't generate a curl in the first place, because only then can you compare these two different equilibria.
So, can I ask, is that,
I'll give it next.
okay. Yeah, thanks. So, despite the fact that when I saw your formalism yesterday, I thought of Jasinski. What you're telling me today is that it's actually, if I look at Jasinski as a way to generate non-equilibrium from equilibrium, the analogy is limited just because of the lack of this gauge invariance type of thing in your the gauge invariance in your business. Is that?
Well, it's so that only part of the observables make sense in the
Yes.
after this translation. So with this extended gauge invariance, part of observables are still computable. And of course, it's no surprise which ones they are. They are the entropic ones, right? The entropy doesn't care about this. This is a pure information theoretic measure of how wide a distribution is or how narrow a distribution is. That survives. And the other thing that survives is that the heat flux, because the heat flux doesn't care about the vertical movements of the entire landscape, but things like work, free energy.
So Jasinski
and
doesn't
so on.
really work.
One version.
Yes.
You can write Jasinski in many ways that are equivalent in the statistical thermodynamics way. So there's all these reformulations of Jasinski. In terms of the subset, still makes sense after the mapping.
Yes, I don't know whether it's related to Mukund's question, but in the conventional Jasinski relations, the underlying process has to be Markovian. Now, I don't understand if there's any strong sort of reason to say that evolution is also a Markovian process, in which case you could make these analogies.
Well, our formulation here, it is a Markovian
I
process, right?
understand,
Because
yes.
there are mutations, there is drift, which is kind of a sampling that goes generation by generation, and there is selection, which this is a modification of these transition rates. So this process that we've written down is a good Markovian process, and you can do it. You can write this. It was for mere convenience that I've chosen sort of the continuum language. You could think of this as really just in this discrete space of population fractions, and then you get hopping rates, and then you have a standard Markov process. Now, of course, the question is, are there more general ways of thinking about evolution that could be non-Markovian? And clearly, if you think of backfirings, well, actually, the example on Tuesday is not completely Markovian in that sense. And that's because the epidemiology of influenza remembers a larger time span. So we're going to see a non-Markovian example.
I think we should take back this feedback.